Thank you for attending this session. Today, we will cover linear programming. You were given videos to watch, and the video shows the solutions to linear programming using the graphical method. The limitation of the graphical method is that it can only be used when there are two variables. In reality, you can have hundreds of variables, but you can't solve those graphically. How do you solve a linear programming problem that has hundreds of variables? In that case, it's going to take the solver command to help you to determine what the solution is. So you viewed those videos, and now we will perform mathematical programming to determine the solution to those graphical solutions. We're going to use mathematical programming instead of solving these problems using the graphical solution. So here is a screen print of the first video that you viewed. If you can see where I'm circling here, this is a formulation of the problem. And again, you need to formulate a problem before you conduct your mathematical programming. In many cases, formulating the problem is the hard part. So understand that that is something that you need to go out there and put a lot of effort into to make sure that the formulation is correct, because if it's not, you're not going to come up with the correct solution. So again, put the proper amount of effort into formulating the problem. So you saw then in this video, this was the formulation of the problem. We want to maximize the profits for these two products, A and B. The profit for product A, which is depicted as X here, is $20 per unit. For problem B, which is shown as Y, is $15 per unit. So the question becomes then, what is the optimal amounts of X and Y that we should sell to maximize profits given the current constraints? And here are the constraints. Here are the budget constraints for the two products. It costs $200 per unit to construct product A. It costs $150 per unit to construct product B. And total demand for A and B has to be less than or equal to 500 units. So what is the optimal amount of units that you can construct that will maximize profits while still meeting the constraints? Maximize the profits while still meeting the constraints. So we will employ then mathematical programming through the solver command to see if we can come up with that solution. I've set up this table here, but now I will go through the process of filling it out and using it to determine the optimal amounts of A and B to construct. Here's the objective function here. we want to maximize this. So let me just type in here. We want to maximize. For the X coefficient, the profit is 20. Remember, that's for product A. And right now, I'm going to set X equal to 1. For the Y variable, or remember that's product B, the coefficient is 15. We'll set that equal to 1. Nothing on the direction here. And let's then write the equation for the objective function. So this will be equal to, remember to cell reference now, this will be equal to, left parentheses, 20 times 1, right parentheses, plus left parentheses, 15 times 1, right parentheses. You should never type in a number into that cell. The cell should be all a cell reference. You need to cell reference every number within the cell there. So the same thing now, we'll go to the constraints. We'll go through this with the constraints now, but with a little bit more description. Oh, so again, this is saying then that if we sell, right now, if we sell 1 unit of product A and 1 unit of product B, our profits will be equal to $35. Is that the maximum? Let's use mathematical programming to determine if that is. And again, we have constraints that we have to program in also. So first then, let's focus on the budget constraint. Let's focus on the budget constraint. So the coefficient, 200 times X, that's for product A. So the X coefficient is 200. And now, be smart on your programming. Cell reference. What is X going to be equal to? It'll be equal to the X that is in the objective function. It will be equal to the X that is in the objective function. What is the cost of production for Y, which is product B? 150. And again, for this cell, it should be a cell reference. This is for product A or Y. Cell reference. Don't type a number in there. Cell reference to the Y in the objective function. Okay. Now in this case, this has to be less than or equal to, let me format this. And again, now I can just copy this down, but the result is going to be 200 times 1 for now, plus 150 times 1. But I programmed this in this cell. So all I need to do is just copy this down. And we don't really need this, but the constraint is that it has to be less than or equal to 50,000 units. Well, $50,000. Finally, let's do this for constraint number 2, x plus y. The number of products A and the number of products B have to be less than or equal to 500 units. So the coefficient for this x here is 1. Again, cell reference. So this x, this cell will be equal to the cell on top of it, which is 1. For y or product B, again, 1. Cell reference here, this should be equal to 1. The direction, less than or equal. You can see that in the formulation. The result, I'm going to copy down the equation here, or the formula there. You can see how everything there, you don't type a number in at all. Everything is a cell reference. And in this case, this is going to be less than or equal to, and this will be 500. And again, this is just for our reference, so that when we program this into the solver, it'll tell us what those numbers have to be. But again now, let's go back to the x and y in the equations. Again, you see that this cell is just a cell reference. This cell is just a cell reference. Why is that? So that all I need to do is just change this number at the top cell there. What if I made this 5? And you see how this cell and this cell adjust automatically, as do the results. And let's make this 5. Oh, let's try something else. Let's make this 8. And you see how this cell and this cell become 8, the same value that's in the top cell. Now, what if we had decided then to make 5 of product A and 5 of product B? If we did that, our profits would be equal to $220. Our total production cost will be equal to $2,200. This is less than the $50,000. So this constraint holds. And again, if we make 5 of product A, 5 of product B, the total number of units would make is 13. And again, this is less than the 500 that is the constraint. So if we make 5 and 8, it's a feasible solution. It works because it meets the constraints. But is it the optimal solution? Probably not. Probably not. But we'll let the computer calculate that for us. Can we go out there and make more than 5 of product A and more than 8 of product B to go out there to maximize our profits? Probably, but how much of each? So we have everything set up now. So now, using the solver in Excel, I'm going to hit Data, look up in the ribbon here, Data, then I'm going to hit Solver, and this dialog box comes up now. Let's go back to our original problem here. This dialog box comes up. So now I want to set the objective. Remember, it's this cell here. So I'm going to set this to I-21. I want to set that to a maximum. I want to set that to a maximum, okay, by changing which two cells. The cell with product A, the top cell, and the cell with product B. Right now that's set equal to 8. You can see it, that's set equal to 8. Oh, I erased everything. We'll set that to a max by changing this cell and this cell, subject to the constraints. Let's add the constraints now that our production budget, which is this cell. So I'm going to add this cell has to be less than or equal to, and from our formulation, the production budget is equal to 50,000. I have to type that in. Let's add the second constraint. So this cell, the demand constraint, has to be less than or equal to, you have a choice here, less than or equal to, equal, greater than or equal to. We'll go over these later. But less than or equal to 500. Total demand for both products cannot exceed 500 units. Then hit OK. So we have the objective function, that's cell I-21. Constraint number 1 is I-22. Constraint number 2 is I-23. Make unconstrained variables non-negative. So we're saying then that X and Y cannot be negative numbers. And we have to choose a solving method. So in this case then, we want to use the simplex method. We'll go over this one, the GRG evolutionary, later. But right now, let's use the simplex method. You have to specify that within the solver dialog box. And I think now then that the dialog box is complete. So we will hit solve. Looks like everything's going to work. And what does that tell us then? And we saw that from the video also, right? What are you going to do based off these results here? You're going to make 250 of product A, nothing of product B. 250 of product A, nothing of product B. In that case, you're going to go out there and your profits will be 5,000. Your production budget will be equal to 50,000. So you hit the upper limit on this constraint, and the total demand will be equal to 250 units produced, which is less than the 500. The optimal combination of product A and product B that this company should produce is 250 of product A, 250 units of product B, none. I'm sorry, 250 units of product A, none. of product B. You can try any combination of X and Y that meets the constraints. You can come up to 5,000, but you will never exceed 5,000. 250 of product A, 0 of product B is the optimal solution. Is the optimal solution. Okay, so let's try this again. Let's try this again with this video that you saw. So we have everything set up here again down here. And we want to maximize the profit function. Again, we have two variables, X and Y, subject to the constraints. Now, I'm not sure what these constraints are. So 2x plus y is less than or equal to 100. X plus y is less than or equal to 80. Okay, so again, we have two constraints, and you're not limited to just two constraints. You can have many more, okay? But you have to make sure to correctly program that in. So you saw this in the graphical solution to this in that video, in that previous video. So let's go out here then and use the solver command again to determine what's the optimal combination of X and Y to produce, to maximize your profits. So again, let's do data, solver, and I'm going to now reset everything. Okay. So we want to set this up. Oh, I'm sorry. Let's formulate this within the cells first. Let me close this. So let's formulate this within the cells first. It's not going to let me. That's okay. So the objective, we want to maximize and just solve this. Okay. So we want to maximize this objective function the coefficient for x is equal to 50. Let's set the first x equal to 1. That's arbitrary. We could have set it to anything. The coefficient for y is equal to 18. The number of y variables, we'll just set this to 1 right now. There's no direction. And the equation then, we have to program that in. So again, make sure that these are all cell references, equals left parentheses 50 times 1, right parentheses, plus left parentheses, 18 times 1, right parentheses. So that's the equation. That's the equation. And again, everything should be a cell reference. Everything should be a cell reference. So 68. So if we made 1 unit of product X and 1 unit of product Y, our profits will be equal to 68. We want to see if we can increase those profits. So for constraint 1, we have 2x plus y is less than or equal to 100. So let's put the x coefficient equal to 2. This value for x, again, don't type in a number. Cell reference to the first x. Right now that's equal to 1. For y, the coefficient is 1. Cell reference y to the first y in the objective function. Okay, the direction is less than or equal to the equation then should be 2 times 1 plus 1 times 1. We should come out to 3. Okay, and this constraint number 2, should be less than or equal to 100. Constraint number 2, the coefficient x plus y is less than or equal to 80. The x coefficient has a value of 1. Again, cell reference. The y coefficient has a value of 1. In this cell reference. The direction then is less than or equal to this equation. I'm going to copy it down. And again, you could see that this equation is all cell referencing. You never type a number in. So it's going to be equal to 1 times 1 plus 1 times 1. Should come out to 2. This constraint, we don't need this really in the solver, but we want to then, just for our reference, we know that constraint number 2 has to be less than or equal to 80. Less than or equal to 80. Let's test to make sure that this was programmed correctly. So if it's just 1, 50 plus 18, 68, yeah. 2 plus 1, 3. 1 plus 1, 2. So everything looks good there. Let me change this x at the top to any number. I'll change it to 5. All these become 5, and the results change automatically. Let's change this one to 10. All these are 10, and the results change automatically. So right now, the interpretation is if we make 5 units of x and 10 units of y, the profits will be equal to 430. Constraint number 1 will be equal to 20. So that's less than the upper level of constraints. So we're within the feasible region. Constraint number 2, the result is 50. We are less than the upper limit of 80. So we meet the constraints. Basically, x equal to 5 and y equal to 10 is a feasible solution based off the constraints. But is it the optimal solution? That's what we want to determine. Is it the optimal solution? That's what we want to determine. Okay. So let's go back to our solver command again. So data, solver. Okay. We reset everything. So now we want to set the objective, and that's going to be equal here to cell I-46. To a maximum by changing which cells? Cell E46 and cell G46. So the first one is E46, comma, and then point to this, G46. Subject to the constraints, we need to add the first constraint. Constraint number 1 has to be less than or equal to 100. Let's add another equation for constraint number 2. Cell I-48 has to be less than or equal to 80. Let's hit OK. Make unconstrained variables non-negative, so check this box. And again, of the methods that we want to use, let's choose the simplex method. It looks like everything in the dialog box is correct. Let's hit the solve button now. So let's solve this. And hit OK. All right, so on this one then, if we produce 50 of X and nothing of A, total profits will be maximized at 2,500. Constraint number 1, the result is 100, which is less than or equal to the constraint. So we make this constraint, but it hits the top level. Constraint number 2, the value becomes 50. It meets the constraint of less than or equal to 80. So for this problem, the optimal combination of X and Y are 50 of X, 0 of Y. 50 of X, 0 of Y. And that's the best combination you can come up with. And just to prove it, let's say we have to stay within 80 here. So how about if I made this X is equal to 50 and Y is equal to 30? So we're going to get, if that's the case, we'll get profits of 30, 40. Constraint number 2, 80, is less than or equal to 80. But you can see constraint number 1, if we have a combination of 50 and 30, the result is going to be 130. which is greater than the upper limit. So this solution is not feasible because it's violating this constraint. It's violating this constraint. Basically, this 50 of x and 0 of y for this particular solution is the best, is the optimal solution. You can't do better than that while still staying within the constraints. You can't do better than that while still staying within the constraints. Okay, so let's try another one now. And let me see, let me do the data solver here. Let's clear all of this. So let's try this problem then. And you saw the video for this one. So this one is a minimization problem. So we want to, here's the objective function where we want to minimize 5x plus 7y. 5x plus 7y. Okay, so same setup. Now, for the objective function, this one is a minimized problem. We're doing a couple maximization problems, but here, let's say that what we want to do is to minimize the costs. So we want to minimize the costs. The x coefficient is 5. Let's set x equal to 1. The y coefficient is 7. You see from up here, it's equal to 7. Let's set x equal to 1. And the result then for the objective function right now, this is equal to 5 times 1 plus 7 times 1. And that should come out to 12. So it looks like we had done our objective function correctly, the results. Now, you see here, these are the constraints. Y is less than or equal to 4. 5x plus 2y is greater than or equal to 10. X plus 3y is greater than or equal to 6. So in no particular order, we just have to list these three. Order isn't important. So let's start with this easy one first. So this top one here, there's no x there. So let's just put 0 for the coefficient. You still have to cell reference to the top cell of the variable. We have the y coefficient, 1, and we have to cell reference to the top value for y, which is 1. Okay. The direction for this is less than or equal to 4. And again, we can copy down the results. So I'm just going to drag this cell down. And we see that, again, you never type in numbers. Every cell, every every figure is a cell reference. Every figure is a cell reference. So when we hit enter, it's going to be 1. That makes sense. 0 times 1 is 0, plus 1 times 1 is equal to 1. Okay, so that works. And again, this constraint then has to be less than or equal to 4. Let me just copy this down. Oh, I put this in the wrong place. So this constraint must be less than or equal to 4. And again, where am I getting that 4 from? Right here. Just from the picture. Just from the picture here. Okay. For constraint number 2, we'll just go with this one. 5x plus 2y has to be greater than or equal to 10. So x, the coefficient is 5. This has to be a cell reference to the cell on top of it, cell reference. The y coefficient is 2. Cell reference to the cell for y, cell reference to the cell on top of it. And now this one has to be instead of a less than or equal to, this one's going to be a greater than or equal to. We'll copy this equation down. Okay. So 5 times 1 is 5, 2 times 1 is 2, so that's 7. And again, the constraint is that this equation has to be greater than or equal to 10. Finally, we have this equation here. X plus 3y is greater than or equal to 6. So the coefficient for x is 1. Cell reference, the value for x, cell reference to the cell on top of it. The coefficient for y is 3. The value for y, cell reference to the value on top of it. The direction is greater than or equal to we want to copy the equation down. And this constraint has to be greater than or equal to 6. The 6 is coming from the picture here. The 6 is coming from the picture. Okay, so you could see here, if we have x equal to 1 and y equal to 1, okay, that doesn't work. X equal to 1 and y is equal to 1. Right here, that's going to put us right here. Okay, why doesn't that work? Because if x is equal to 1 and y is equal to 1, it violates constraint number 2. 7 isn't greater than 10. And for this one, 4 is not greater than or equal to 6. 1 and 1 is right here. The feasible region based off of these constraints is the blue area. Okay, so let's try another one. What if we had x is equal to what do we have down here? Let's make this 6. 1, 2, 3, 4, 5, 6. I'm sorry it got cut off here, and we'll make y is equal to 3. So x is equal to 6. Y is equal to 3. See how everything will change for us automatically. So we see here then that the cost, what we're minimizing, is 51. All right. 3, constraint number 1. Yeah, we meet the constraint. 3 is less than 4. 36. When x is equal to 6 and y is equal to 3, constraint number 2 is equal to 36. Yes, that's greater than the 10. And constraint number 3, 15 is greater than or equal to 6. So that's going to put us then, if we have x is equal to 6 and y is equal to 3, it's going to put us right here. Going to put us right here in the feasible region. However, is that the best result? Is that the best result? Is that the optimal result? Let's perform mathematical programming to see if that's true. So we'll go data, solver. I think everything should be cleared out now, and that's true. So we want to set the objective function. That's going to be equal to cell I-71 in this instance. We want to set that to a minimum. We want to set that to a minimum by changing cells. Which cells do we want to change? X, which is going to be equal to cell E71, and G71. E71 and G71. We want to add the constraints. So this, first off then, for constraint number 1, we want to add this cell has to be less than or equal to 4. Let's hit OK. Well, let's add another one. I'm sorry. Constraint number 2, this cell, I-73, has to be greater than or equal to 10. Let's add another one. So cell I-74 has to be greater than or equal to 6. Let's see if we have everything in there correctly. Yeah. So the 4, 10, and 6. Make these unconstrained variables non-negative. Simplex method. Let's hit solve. Looks like everything is okay. So if you remember from that video, the presenter used the substitution method to determine the optimal values of x and y. And he then determined that x is going to be equal to 1.38, y is going to be equal to 1.54. We got the exact same solutions that he did. Okay, and so hopefully that's kind of proof that the answers that he got, the using mathematical programming, that will give us the exact same type of solution. Okay. We replicated the results, and this one's a little bit better because you could see what the feasible region is. Right. The only thing is that it didn't really have the problem formulated in the correct fashion, but they gave us enough information where we could determine the equations to feed into the computer. All right, and then we had one more here. Problem you had to, we have another one here, another minimization problem. So let me go through this one quickly then. So this one was done using the graphical method. We want to, here's the objective, so we want to minimize this one. The x coefficient is 3. And they do x2 here. We'll just make that, we'll set this one equal to 1. And how about this? Well, let's do this so it won't be as confusing. So this will be x1. This is x1. This is x2. This is x2. Okay, and 2. You can see that the coefficient is 2. And we'll just set that equal to 1 for now. And the results are going to be equal to 3 times 1 plus 2 times 1. That's equal to 5. Here are the constraints now. So we have 5. Here's the first constraint here, 5. Again, cell reference to the top cell. X here is equal to 1. Cell reference to the top cell. Okay. This one is a greater than. Let's copy down the results. And the limit is that it has to be greater than or equal to 6. The second constraint, oh, I'm sorry. This one has to be greater than or equal to 10. In the second, x1 plus x2 greater than or equal to 6. We can just copy all this down now. So this is going to be x1 plus x2. Coefficient is 1. We'll set these equal to 1. This one, constraint number 2, this is the one that has to be greater than or equal to 6. And we'll just copy this down one more time. X1, the coefficient is equal to 1. X2, the coefficient is equal to 4. And x2 has to be greater than or equal to 12. Greater than or equal to 12. Let's do the solver. Data. solver. The objective is cell I-95. I want to set that equal to a minimum by changing cells. The first one is E95, then G95. So we'll change those cells. Let's add the constraints. So we want to add that this cell has to be greater than or equal to 10. Let's add another one. This cell has to be greater than or equal to 6. And let's add one more. This cell has to be greater than or equal to 12. Hit OK. Okay, so 10, 6, and 12. It looks like our inputs are correct into the dialog box. Make unconstrained variables non-negative. Select a solving method. Hit solve. Hit OK. And so to minimize this, the lowest number we can get is 26. That's the lowest value we can get. By producing 8 of x1, 0 of x2. And we could see that it meets this constraint, it meets this constraint, and it barely meets this constraint. It barely meets constraint number 3, but it meets the whole set, the 3 sets of constraints. So x1 equal to 8, x2 is equal to 0. Those are feasible solutions. Any other combinations of x1 and x2 will give you values greater than 26. You can't come up with a value less than 26 and still meet all the constraints. You can't come up with a value of less than 26 and still meet all the constraints. So that concludes then this session. Thank you for watching, and contact me if you have any questions. Thank you again.